Good afternoon, students. Since we already completed chapter 1, now from this lecture onwards, let's start chapter 2. This chapter 2 is also related with chapter 1. We need to use all the concepts which we discussed in chapter 1 in this chapter 2 also. Chapter name is Electrostatic Potential and Capacitance. So first let us discuss what is electrostatic potential and electrostatic potential energy. Based on that we can move. So before going to electrostatic potential, first I will discuss electrostatic potential energy. From that I will discuss what is meant by electrostatic potential. Okay, so let us first see what is meant by electrostatic potential energy. So this is the definition for electrostatic potential energy. Electrostatic potential energy of a charge Q at a point is the work done by the external force in bringing the charge from infinity to that point. Let us see what is meant by this statement. In order to explain that, consider a charge. Here it is Q, so that we can consider a charge at P, or let us say P. Charge is Q plus Q. Okay, your charge is at P. Now you are having another charge here. This point is R. You are having a Q charge here. Okay, so now you know that whenever there is a charge, it will exert an electric field. Okay, so you are having a Q charge here. This Q charge will have its own electric field. Okay, so that you can draw its electric field will be there. This is the electric field due to your charge Q, which is at R. Now you want to move this charge Q, which is at P. You want to move it from P near to R. Okay, or particularly you can take a point. You want to move the charge Q, which is at P, from there to another point which is S. Okay, so you want to move the charge Q from P to S, but you can see that S is near to R. So the electric field of this charge Q at R will be acting at S also, because you can see electric field is moving like this. S is in that electric field, so the point S is in the electric field of Q. Hence, if you keep a charge at S, it will also experience this electric field produced by the charge Q at R. Okay, so for explanation simplicity, we considered both R plus Q. Now imagine that you are trying to bring this Q at P to the point S. Now what happens? You are already having a charge Q at R. You are trying to bring another Q from P to S. If you move it like this, moving towards S, what happens? This Q will exert a repulsive force, because this is a positive charge, this is another positive charge. They are like charges, that will be repulsive force. So this Q will exert a repulsive force on this Q. Hence it is not easy to take this charge from here and place it here. Okay, but you need to take it from here and you want to place it here at S. where it will get repulsive force. Okay, so you need to do this activity means you need to do external work, because you need to overcome this repulsive force given by the electric field. Here this charge is producing electric field. Electric field means the one side will be positive and other side will be negative, isn't it? Last chapter you studied it will move from positive to negative, so that this side will be positive, this side will be negative. Whichever be the side it is going, it is negative. Okay, now you are bringing the charge Q towards R, means your charge will exert a repulsive force, isn't it? Your charge will exert a repulsive force. So that what happens, you need to do extra work, then only you can bring this charge from here to here, isn't it? So you need to do external work. Whatever be the work you are doing to bring this charge Q at P to the point S, that work done is actually stored as the potential energy of the system. System means you are having two charges. Okay, so it will make a system. Hence potential energy is nothing but, potential energy associated with a charge is nothing but the amount of work done to bring that charge from infinity to a point where an electric field is acting. Okay, why we are considering infinity? Because our assumption is that at infinity no electric field will be present. So if you keep it here, it will always be there. No repulsive force will act from this charge, because we assumed that it is very far away. Infinity means very far away. At a very large distance this repulsive force will not act. So here it is infinity, it is very far away. Even though it appears to be near to S, it is in reality it is very far away. Okay, so from a very large distance, that is considered as infinity, if you want to bring a charge to a point near to another charge, you need to do work against this electric field, because electric field is opposing this process. If you want to move it, electric field will oppose, isn't it? So if you want to move this charge, you need to do work against this electric field. Okay, so whatever be the work you are doing against the electric field in order to bring this charge from here to here, that is from P to S, that work done is stored as the potential energy. Okay, and whatever be the work this electric field is doing on your charge, you need to do equal and opposite work. So the work done by you is equal and opposite to the work done by the field on your charge. Okay, now let us consider the case mathematically. So in 11th you studied the equation for work done in terms of integration. It is, if you have a point here, if you have something here at A and you want to move it to B, you need to do work. That work done is nothing but integral A to B dw. dw means f dot dr. This is the equation for work done which you studied in 11th class. Now let us see here that there is a term F. F means you are trying to move something from A to B. So you need to do some work in this situation. Doing work means you need to exert some force. That F is nothing but the external force you are applying. Okay, so this F is nothing but F external dot dr. This is the equation you are having. Now let us apply the same equation here, so that work done by u. U means in order to move your charge plus Q from P to S, let us calculate the work done. Okay, so let us calculate it. Work done to move Q from P to S. That is what you are going to do. You are moving from P to S. It is not an easy process. You need to do work against this electric field. Okay, so you are going to calculate that work done. First write the equation for work done. What is the equation? Integral A to B, initial point to final point. Here initial point is P, final point is S. F dot dr, here F is external force. Okay, now whatever be the force your electric field is exerting, you need to exert equal and opposite force. So let us imagine that electric field is exerting a force of Fe. Okay, force exerted by electric field is Fe. That means you need to exert an equal and opposite force in order to move your charge Q from P to S. So electric field is exerting a force Fe, which means you need to exert a force minus Fe. Okay, so the external force which you are applying is minus Fe. Okay, so I am going to rewrite the equation. P to S, what is F external? That is minus Fe. So Fe I am writing here, minus I am taking out. Okay, now dot dr is there, so let us change it. F dr, F, or that changing we can do later. Now let us write it as it is. F dot integral P to S Fe, there is a minus sign, dot dr, where Fe is the force exerted by electric field. You need to exert an equal and opposite force, that is why minus Fe. So this is the amount of work done you need to do in order to move your charge from P to S, which is against an external electric field. Okay, so this work done, is stored as the potential energy, potential energy of the system. Okay, so that you can say potential energy is equal to minus P to S Fe dot dr. We will represent potential energy using a letter capital U. U means potential energy. It is equal to minus Fe dot dr. Okay, this is the equation for potential energy, minus Fe dot dr, where Fe is the force exerted by the electric field. You need to exert an equal and opposite force, that is why you are taking a negative sign. Okay, and you are not representing it as a vector because potential energy is a scalar quantity. You can see from the equation also, you are actually finding dot product. This is a dot product, isn't it? Dot product between force and displacement. In 11th you studied that dot product end result will be a number, a scalar. If you do this dot product, you will get a number only. There won't be any direction. Number means a scalar. Okay, so potential energy is a scalar quantity which will not have any direction. It will only have some value. Okay, so whenever you are solving problems related with potential energy, you need to consider the sign of the charge also. If it is negative charge, you need to consider negative sign also. While doing problems in electric field and force, I told you that no need to consider the negative or positive sign, that you will separately do with the diagram. Directions you will mark in the diagram. Then in the equation Coulomb's law or some other equations, you will only use magnitude of the charge. That is applicable only for vectors. When you are dealing problems with scalars like potential energy, if the charge is negative, you need to consider the negative sign also. It is a must. Okay, so this is the equation for potential energy, electrostatic potential energy. Okay, which is nothing but the amount of work done by the external force in bringing a charge from infinity to that point. Okay, so if you need to do some 5 joule of work to move this Q from here to here, then that 5 joule will be stored as the potential energy of the system. Okay, if you need some 100 joule of work to move Q charge from here to here, then that 100 joule will be converted as the potential energy of the system. So electrostatic potential energy is nothing but the amount of work done to bring a charge from infinity to a point. At that point we will define electrostatic potential energy associated with that charge. Okay, if the point is S, then at S this much of potential energy will be there associated with the charge Q, like that we will say. Okay, when point changes, potential energy also changes. So at a point we will define potential energy. That's why you can see in the definition also, electrostatic potential energy of a charge Q at a point is the work done by the external force in bringing the charge from infinity to that point. So potential energy will change depends upon the point. At this point S, it is given by integral minus integral P to S Fe dot dr. If the point changes, this limit will also changes, and hence your potential energy will also changes. Okay, so here I forgot to write the letter P to S. Okay, if it is point P and S, if the point is A and B, you are moving from A to B, then it is minus integral A to B, initial limit, final limit. Okay, now in this case I kept a Q charge here. Okay, if instead of Q I kept a unit positive charge at P, a +1 charge, I am not keeping a Q charge, but I kept one +1 charge at P. If it is the case, then I am moving that +1 charge from here to here. Instead of Q charge, I am moving a +1 charge only, a unit positive charge. I am moving from P to S. Now also I need to do work, because it is a positive charge, it is a positive charge, there will be repulsive force. So I am moving in an external electric field produced by this Q charge. I am moving this charge towards the other charge, means I need to do work. But in this case there is a change. I am not moving a Q charge, but I am moving a +1 charge. So I will calculate how much work I need to move it from P to S. The amount of work done needed to bring a unit positive charge from P to S is defined as electric potential. Okay, in the definition of electrostatic potential energy, you are moving a charge Q. So you can see electrostatic potential energy of a charge Q at a point is the work done by the external force in bringing the charge from infinity to that point. Here the charge is Q. Instead of Q, if it is +1, so let us say charge plus 1 at a point, if the definition is like that, then the term will be changed from potential energy to potential. Both are different terms. Potential energy is the work done to bring a charge q from infinity to a point, whereas electrostatic potential is the amount of work done by the external force in bringing a plus 1 charge from infinity to that point. So if the charge is not a plus 1, then it is called as electrostatic potential energy. But if the charge is specifically a unit positive charge which you are bringing, then the amount of work done is called as electrostatic potential instead of electrostatic potential energy. Okay, so this is the definition for electrostatic potential. It is represented by the letter capital V. Electrostatic potential at any point in an electric field is the work done in bringing a unit positive charge from infinity to that point. Only change is that instead of a charge q, you are bringing a unit positive charge. Then the amount of work done is said to be electrostatic potential instead of electrostatic potential energy. So in another way, you can define electrostatic potential as the electrostatic potential energy associated with a unit positive charge. If you bring a unit positive charge, that electrostatic potential energy is called as electrostatic potential. Okay, so if you are having a charge here at P, you are having a plus 1 charge, you are having another charge here Q at R, so it will exert an electric field. Now in that electric field you are considering a point S. Your intention is to bring this plus 1 charge from P to S. You want to move it from here, you want to move it in this direction, and you want to keep it here at S. You want to keep it at S. Then you need to do work. How much work you are doing in this process? That work done is stored as the potential. It is not a potential energy, we will use the term potential. So electrostatic potential at any point in an electric field is the work done in bringing a unit positive charge. Instead of Q, if you are bringing a plus 1 charge, then instead of electrostatic potential energy, you will define it as electrostatic potential. Okay, so electrostatic potential is nothing but the electrostatic potential energy of a unit positive charge. This is also potential energy, but since it is a unit positive charge, you can use the term electrostatic potential. So electrostatic potential is nothing but the amount of potential energy associated with a unit positive charge, or more specifically, this is the definition: the electrostatic potential at any point in an electric field is the work done in bringing a unit positive charge from infinity to that point. So the charge you are bringing must be plus 1. Now you already got the equation for U minus F E dot dr. From this you can find the equation for V. U means potential energy, that is for a charge Q. If you bring a charge Q from infinity to S, so if you are having a charge Q here and you are bringing it to S, you are bringing it to S, then the work done is stored as potential energy U. But if instead of this Q is not there, you are bringing a plus, then the work done is called as potential. So instead of Q, you are bringing a plus 1 charge. Okay, so for Q charge, the amount of work done is W, that is equal to U, because you are doing work and that work is stored as potential energy. So for Q charge, the amount of work done is U. You can say that it is U because work done is stored as potential energy. Then for plus 1 charge, how much is the work done? It is nothing but U by Q, isn't it? Because for Q charge you are doing a work done W, that is stored as potential energy. If you want to use, you can say for Q charge you are doing a W work done. So here also you can write it as W. This W is stored as potential energy U, that is given here. Okay, so for Q charge you are doing W work done. Then for plus 1 charge, how much work you need to do? That is W by Q. This work done you need to do in order to bring a unit positive charge from infinity to that point is defined as the electrostatic potential at that point. Here electrostatic potential at S is nothing but the amount of work done in bringing a plus 1 charge from infinity to this point. Okay, so this is nothing but V. V is electrostatic potential, that is equal to W by Q, where W is the work done to bring Q charge. Okay, so this is the relationship. Electrostatic potential is equal to total work done to bring Q charge divided by total charge, from which you can write it as W is equal to QV. So these are the two terms, electrostatic potential energy and electrostatic potential. Electrostatic potential energy is nothing but the amount of work done to bring a charge Q from infinity to a point. So at that point the electrostatic potential energy is defined as the amount of work done to bring Q charge from infinity to that point. Instead of Q charge, if you are bringing a plus 1 charge only, then the related work done is said to be electrostatic potential. So in such cases, instead of electrostatic potential energy, you will use the term electrostatic potential. So that is the only difference between electrostatic potential energy and electrostatic potential. If the charge is not a unit positive charge, then it is electrostatic potential energy. Work done is electrostatic potential energy. But if the charge is unit positive charge, then the work done in that case is electrostatic potential. This is the difference between both the terms. And based on this, we will move on further. All the topics are related with this only. Now we will find electrostatic potential due to a point charge, then due to a dipole, like that we will move. So only if you understand the concept of potential and potential energy, you can understand the upcoming topics. Okay.